Alright, hello everyone, welcome to the new section on convolutional neural net. So in this section, we will introduce a very famous model. It's called convolutional neural net, or CNN by short. So CNN has been demonstrated to be a very powerful model to handle the images. And in some other areas, people also try to use CNN to deal with natural language processing data as well. So in this section, we plan to provide you with a more detailed introduction about what is CNN and how to use a CNN model to deal with computer vision problems. So here's the outline for today's lecture. In the very beginning, we will talk about how to present the images. Then we'll talk about several conventional image processing operators. And after that, we will introduce a very famous operator. It's called convolution. So the convolution operator will be extensively used in the CNN model for extracting some features by the model automatically. And after that, we will talk about the CNN model architecture as well as putting layers inside this model. Then we discuss several variant models of CNN, and finally we'll talk about another famous model. It's called ResNet. So ResNet tries to learn a very deep CNN with residual learning stage. And we'll talk about all these topics in detail in this section for you. So in the very beginning, how to represent an image. Actually depends on the image we have. We can represent these images with different kinds of metrics instead. So for example, if we have a black-white image like this one, for all the pixels, they can be either black or white. In other words, we can use one single bit to denote each pixel inside this black-white image. And if we plan to represent this image into in Python code, and we can denote this image as a matrix as shown on the right-hand side. And for all the pixels which are white, we can denote these entries with 0, and for the black pixels, then we can denote them as 1 value instead. So in this way, we can convert this image into a matrix with the same dimension, and inside this matrix, they are all binary. And for these kinds of black-white images, we can use one single bit as shown here to represent 1 pixel. And for some other images, they are not black or white, however, they are gray instead. And to denote different kinds of gray scales, we can represent them with some number. For example, on the right-hand side, we show a gray image for us. And for all the pixels inside this gray image, we can represent it as a number, as an integer in the range from 0 to 255. And for a pixel which is very dark, then we can represent it as a small number. And for the pure black pixel, then we can represent the entry with 0. And for the pixel with a white color, we can represent it with a very large number, like 255 instead, right? And for all the other gray pixels, which are between white and black, then we can represent them as an integer in the range from 0 to 255 instead. So you can see, in this way, we can represent 1 pixel as 1 byte instead, because each integer here can be represented with 8 bits or 1 byte instead, right? So in this way, we can represent these gray images into a matrix as well. And besides the gray image, a more common image you can have in the real world, they are all the color image, right? The next at the bottom will show a color image. As we mentioned in the previous lectures, we can also represent a color image into matrices instead, or into a tensor instead. So for this color image, we can represent it as a 3 matrix, RGB, right? Because each pixel or each color pixel inside this image, we can represent it with 3 values, denote its corresponding red, green, and blue colors, right? In other words, so for each pixel in this color image, we can represent it with 3 integers, right? And also for each integer, we can also represent it with 1 byte or 8 bits. So therefore, we can use 3 bytes to represent 1 pixel inside a color image. And this color image can also be converted or represented as a 3 matrix on the right-hand side, RGB, right? As shown here. So these are the common way to represent the images in applications. Depending on the category of image we are studying, we can either start the black-white, we can represent them into a matrix as binary matrix, or we can represent a gray image into a matrix with the values in the range from 0 to 255. Right, and for the color image, we can represent them into 3 matrices denoting the RGB coding for the pixel inside this image. So based on these matrix representations, we can learn something from these images, right, with deep learning. As we talked about this multi-layer perception model before, we mentioned that we can classify the images with this MLP model, right? So given this column image, we can represent it into these RGB matrices. And these matrices can be further converted or can be reshaped into a vector, denoted by this vector, right? We can have this serialization of all the pixels inside RGB matrices into vectors. Now, this region denoting this radar, this matrix, this region corresponding to the green matrix, and the bottom part denoting the entries in the blue matrix instead, right? So by serializing this matrix into a vector, we can further feed this input into a multi-layer perception model as input, right? So we can feed these numbers into this input layer, and we can further propagate these inputs into the hidden layers, hidden layer 1, hidden layer 2, hidden layer 3, and further go to the output layer. Then in this way, we can classify the potential objects inside the input images, and we can recognize this cat from the image by classifying it. Okay, so this is what we have introduced before actually in the previous lectures. Actually, if you have ever taken a look at the project study 2, you have also do this already. If you take a look at the dataset we provide for study 2, actually the dataset we have provided you in the study 2 is about the image dataset. Even though we have serialized this image into a vector already for you, if you have ever tried to reshape the vector in study 2, you actually find that actually we are providing with a dataset covering the images of the hand return numbers. They are all the grayscale images instead. So again, we will try to use the same dataset in the stage 3 as well, so you can compare your performance in stage 2 versus stage 3, and then you can have understanding about the performance of both MLP and CEM model to be studied in the stage 3, and you can compare them with each other to see their performance difference. Alright, so this is what we have introduced with you already, in the previous lectures. So actually, if we try to use this MLP model to do this image classification, we can do this. But we also have some shortcomings because of this MLP model architectures. And we observe some weakness with the MLP model when we are dealing with image dataset. So first of all, this MLP model is insufficient for modern advanced computer vision tasks in many more complex domains. Now we may have the image dataset from the self-driving cars like Tesla. The dataset we have will be much more complex. And if we are training this MLP model to deal with this complex vision dataset, then this model architecture is not sufficient to do more complex tasks. And also for the MLP model with hidden layers, we will have too many parameters to learn. Now for the images with the size of the m row and n columns, then the number of pixels inside this image will be m times n, right? For the gray images, or 3m times n for the RGB color image instead. And if we are feeding these larger numbers of pixels into the input layers for MLP, then this input layer will be very large, right? And for learning this kind of large input layers, we normally need to have more hidden layers with also large dimensions. So with more hidden layers, then we have too many parameters to learn for this MLP model. Normally for a model, if we have too many parameters, we may require lots of data to learn these parameters, right? Also, the learning cost will be very high. And also, in many cases, we may suffer from these overfitting problems or not. So this is also the shortcoming with the MLP model. And for the third weakness, for the MLP model, when we are serializing this input image into a vector, actually we are discarding the spatial information inside the image, right? In other words, we are converting these pixels, which may have some correlation with each other, into a vector with independent elements, which may result in the discard of the spatial information inside the image actually among the pixels. So because of this weakness, then we may call for some new models to deal with images, which will be covered in this section on the convolutional neural nets.